Hi class, in this video here we want to look at section 2.3 from the textbook, and it's titled Prime Cuts of Numbers. And so what it's going to introduce us to is talk about how prime numbers are the building blocks of all the natural numbers. And so just so we're clear, what are the natural numbers? They're the numbers 0, 1, 2, 3, 4, and going on then for infinity. Okay, so think about it as like the counting numbers plus 0. Okay. All right, so what exactly is a prime number? So a prime number is a natural number that can only be divided without a remainder, so there's no remainder, by itself in one. In other words, prime numbers have exactly two factors. Okay, so for example, 13, if you think about 13, the number 13, you can only divide it by itself. 13 divided by 13 gets you 1, and by 1. 13 divided by 1 is 13. Okay, so that's what's the definition of a prime number. So what are the prime numbers between 1 and 100? And just note, you might think 1 is a prime number, but it's actually not, because it only has one factor itself, right? So here are all the prime numbers between 1 and 100. So it starts at 2, 3, 5, 7, 11. I won't write them all out or say them all out, but they're all listed right here for you. So these are all just numbers. Like if you look at like 23, okay? 23 can only be divided by itself, 23 and 1. That's it, nothing else. All right, so it turns out that every natural number greater than 1 is either a prime number, okay, or it can be expressed as the product of prime numbers. And so a product is multiplication. All right. So for example, if we look at the following numbers, all right, 12, 30, and 40. If you look here, 12, 30, and 40 are not prime numbers. What this is saying is you can write these numbers as products, so multiplication of prime numbers. So for example, we know 12. 12 is equal to 4 times 3. 3, looking back, 3 is a prime number. But wait a second, 4 isn't, right? 4 is not. But then what I notice is that 4 is the same as 2 times 2. So look, 12 is the same thing as 2 times 2 times 3. And all of these numbers right here, prime numbers. If you look at 30, right? 30 I can write as 3 times 10. Well, 3 is a prime number, but 10 is not. But 10 I know is 2 times 5. And 2 and 5 are both prime numbers. So 30 is the same thing as 2 times 3 times 5, the product of prime numbers. 40 is 4 times 10. And well, look, 4 is not a prime number, 10 is not a prime number, but what we just saw with the two examples above, 4 is 2 times 2, 10 is 2 times 5. So 40 can be written as 2 times 2 times 2 times 5, the product of prime numbers. So if a number is not a prime number, it can be written as the product of primes, which is like a really cool little trick with numbers. You know, like as we've been seeing working through the textbook, there's all these interesting little, patterns or properties of numbers, and numbers, natural numbers that are not prime can be written as a product of primes. All right, so it turns out when we talked about the infinitude of primes, that there's actually an infinitely many prime numbers. Now, if there's an infinite number, I can't list them all right because it goes on forever. So, every day we're still finding new prime numbers. So you may wonder how the primes are distributed among the natural numbers. Basically, what I'm asking, is there a pattern to the distribution? There are infinitely many prime, but like how rare are they among the numbers? So like what proportion or what percentage of natural numbers are prime numbers? Is it a half? Is it a third? I mean, I don't know, right? So if you look at the first 24 natural numbers, okay, right here, 9 are primes, okay? So we see that 9, so look at the first 24, the numbers 1, 2, 3, 4, 7, 11, 13, 17, 19, 23, okay? 9 of them are prime. All right, so if you take 9 divided by 24, that's, turning it as a percentage, it's like a little under 38%, okay? So just a little over a third, okay? So extrapolating from this observation, could we guess that just over a third of all natural numbers are primes? Like what percentage? So if you look at the first, what n represents is the first n numbers. So the first 10 natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right to here, right? 4 of them, 1, 2, 3, 4, And I'm sorry, what I mean by the first natural numbers, if you look at 0, 1, 2, 3, 4, 5, 6, 7, 8, up to 9. Zero is not listed there. Sorry, apologies for that. But 2, 3, 4, and 7, okay, are prime numbers. So 4 out of 10 is 40%. All right. If you keep doing that, you look at the first 100 numbers, 25%, or 25 of them are prime numbers. So 25%. But as you continue to increase, all right, look at the first 1,000 numbers, 10,000 numbers. These are the number of prime numbers. The proportion continues to fall. All right. And if you look here, it looks like it's converging to something. Is it like, oh my gosh, look, it looks like it's converging to around 5%. But look, it keeps falling. So, like, does it, what I'm trying to hit at is, does this hold? Is it true that like roughly 5% of numbers are prime numbers? No. Okay. So we have this thing called the prime number theorem. And it says as the numbers you look at gets larger and larger, the number of prime numbers less than or equal to n, it actually approaches this formula. You take n and you divide it by ln of n. And what ln is the natural log. Okay. So on your calculator, you would see an ln button. So if you look here, and this is for taken from the textbook, this is the first billion numbers. And the first billion numbers, okay, roughly 50 million of them are prime numbers. That's crazy. All right. Well, now let's look at the first trillion numbers, first trillion natural numbers. Okay. What would happen then is if you took the proportion of prime numbers is equal to this, you would take 1 trillion, divide it by the natural log of 1 trillion. And you would see that if you look at the first trillion numbers, the proportion of them that are prime, it gets very, like, it's incredibly small. So what I'm hinting at is there's a lot of prime numbers initially, but then as numbers get bigger and bigger and bigger and bigger, it gets rarer and rarer to be a prime number. They still exist. There's, but a very, very small proportion of incredibly large numbers are prime numbers. All right, class. I hope this lecture was a good introduction to prime numbers. As always, your textbook will flush out a little bit more detail all of this, and I'm always here for help or questions.